Okay, I'm going to try something different here. I've got a PowerPoint. We're going to be talking about residuals and residual plots. Okay, one of the first principles of data analysis is to look for an overall pattern and for any big departures from that pattern. A regression line describes the overall pattern between the explanatory variable and the response variable, or between x and y. But it also assumes that there exists a linear pattern. We can see departures from the pattern by looking at the residuals. Residual analysis allows us to test the assumption that a linear pattern exists. So we're going to be testing it. Okay, so what is a residual plot, and what is the purpose of a residual plot? A residual plot is a scatter plot of residuals against the explanatory variable. So we're going to make a scatter plot, but instead the response variables, we're going to use the residuals. And it helps us to assess how well a regression line fits the data. What two important things do you look for in a residual plot? Well, the residual plot should show no obvious pattern, and the residuals should be relatively small in size. How can we tell if a linear model is appropriate? Well, by checking to see if the residual plot has no obvious pattern and that they're relatively small. We need to also look for outliers, and etc. And I've got some, I found this online, and it will kind of give you an idea of what these look like. Okay, so here's a regression line, and this would be the residuals. Note that our residuals should all add up to 0. So that's why we're going across the line of 0. This residual plot shows the position of the data relative to the regression line. In fact, the horizontal line of the residual plot is the line of 0 residual, which corresponds with the regression line. So this is going to correspond with our regression line. If a straight line is appropriate model for the data, then the residual plot should display random scatter with no obvious pattern. This seems to be the case here. So there's no pattern here. It's just all over the place. No big outliers. Okay. At first, the first thing to look for in a residual plot is outliers. Points with very large residuals, either positive or negative. A single outlier can have a large influence on the line of best fit. Here, the response y, when x equals 40, is much lower than expected. The residual is almost 50, which is more than twice any other residual. So this is kind of a sign that something's wrong, and we maybe shouldn't be using a linear model. Here we see an outlier at x equals 5, clearly out of line with the rest of the data. Note how the regression line has been pulled toward that extreme point. It's being pulled up. As well as a large positive residual, notice the upward trend of our data. This is clearly not random scatter we are looking for. So probably not going to use a trend line. Okay. At first sight, this regression line looks to be a reasonable fit. the points are all fairly close to the line. However, the residual plot magnifies the deviations from the line and reveals a different story. If you look, you got a whole bunch of data going here, a whole bunch of data going here. So this is probably not going to be a linear model. Again, the points are all fairly close together, but look what happens to our residuals. Okay, this obviously has a pattern, and if we try extrapolating using the line, the regression line, we're probably going to have some really bad predictions. So, not a good idea. Okay. At first sight, this residual plot looks random, but take a more careful look. If you look at the points, it looks like we got three patterns going from high to low. This is not going to make a good linear model. It's not random. Okay. The most notable feature of this data is how large the variation is about the line. This is reflected in our residuals. Okay, there's no obvious pattern here, but you can pretty much tell that that this is going to be a very weak association anyhow. Okay, here we see that for the small values of x, the points are closer to the line, where the big values for x, they're further apart. The fanning out of points on a residual plot is a clear sign of non-consistent variance. The residuals should form a constant band and not kind of like that trumpet shape where it's going out at the end. Okay? This looks like it's going to be a really good linear model. But if we look at the residual plot, you can see that this is not random. Okay? So this is not going to be a good linear model. Even though it looks linear, don't trust it. Okay, so it says construct and interpret a residual plot for track and field day data. All right, so here is our track and field day data. Here's our sprint time and our residuals. Remember that on a residual plot, we are using our residuals instead of our Y values. So when I plot that, this is what it looks like. Well, looking at this, I've got an outlier here. Even though a lot of this looks like it might be random, we've got this outlier. So this is probably not going to make a good linear model. All right? Now would be a time to stop and check for understanding on page 176. Okay, find the residual for the subject who increased NEA by 620 calories. Show your work. All right, so we can predict the fat gain for this person is to be 1.3722 kilograms. So the residual is 2.3 minus 1.3772, and we get 0.9278 kilograms. Interpret the value of this subject's residual in context. All right, the residual says that this person gained 0.9278 kilograms more than we would have predicted using the least squares line as a model. For which subject did the regression line over-predict fat gain by the most? Justify your answer. All right, the line over-predicted the fat gain the most for the person who had the NEA change of 580 and a fat gain of 0.4. that person's predicted fat gain is 1.51 kilograms, and so the residual is a negative 1.11 kilograms. Based on the list of residuals given in the previous example, this is the largest negative residual and therefore the point for which the fat gain is most overpredicted. Okay, so what is S and how do we calculate it? S is the standard deviation of the residuals. We calculate it by taking the square root of the sum of the residuals squared and dividing it by n minus 2. So S is the sum or the standard deviation of the residuals. We calculate it by, remember that the residuals are y minus the predicted y, or y hat, squared, and we're divided by n minus 2. If you're wondering why we are using n minus 2 instead of n minus 1, you'll find out that until chapter 12. So just be patient. You'll find that out. All right, checking for understanding. Now would be the time to stop and check your understanding. Okay? The residual plot does not show a random scatter. Describe the pattern you see. Okay. There is a moderate positive linear relationship with one outlier in the bottom right corner. That outlier is what's making it not a random scatter. Okay. For the regression S equal 2.27, interpret this value in context. The average error, or residual, in predicting the backpack weight is 2.27 pounds, using the least squares regression line. Okay, suppose that a student was absent on the day these data were collected. Predict this student's long jump distance. Well, that'd be great. It'd be so much easier if we could use the line of regression, but we don't have the student's sprint time. So what should we do? Well, probably the best strategy is to use the mean jump distance of the other students. Now, that would be if this is a really strong correlation, and we need to check that. So what we're going to do is find R squared. Well, what is R squared and how do we calculate it? The coefficient of determination, that's R squared, in a regression is the fraction of the variation in the values of y that is accounted for by the least squares regression line of y on x. We calculate it using this formula. R squared is equal to 1 minus SSE over SST, where SSE is the sum of all the residuals squared, and SST is the sum of all the y's minus the mean squared, quantity squared. How are R and S squared the same? And how are they different? Both S and R squared are calculated by the sum of the squared residuals, and both measure how well the line fits the data. However, S is expressed in units of the y variable, whereas R squared is expressed as a percent between 1 and 100. What is SE and SST in that formula? SSE is the sum of the squared errors, the sum of our residuals squared. SST is the total sum of the squares. How are SSE and SST the same and different? They both are the sum of squares, and SSE is the sum of the squared residuals, and SST is the sum of the squares of the difference between the actual observations of y and the mean of the observations. Okay, so now would be a good time to stop and check for understanding on page 181. Okay, the answers to those questions are C and D. Okay, so I kind of wanted to go over a little bit about this, about R squared with you and how it works. This is a set of data, and it's linear regression line, least squared regression line. It has a correlation R of a negative 0.944. So there's another set of data, and it has a linear regression line with a correlation R of a negative 0.79. Both of these are linear models. We want to know, and these are our linear models for those two sets of data. We want to know which one of these, which value for y is more accurate of a prediction for the given x. Well, to find that, to find out how well the line of best fit actually fits the data, we can find a number called R squared by using the following formula. Now, they have it written out in words. It's 1 minus the squared differences between the actual and the predicted y's. Remember, that's how we found our residuals. And then the sum of the sum of the squared differences between the actual y and their mean. So here we've got this line, and the line of best fit is y. Of course, this is y hat equals 0.94, actual 4, x plus 43.7 with a correlation of a negative 0.44. There's our table. So we're going to take our table, and we're going to find our predicted value of y. So we would substitute that in each of our x's into the formula to find the predicted value of y. Then we're going to find the error, which would be the actual minus the predicted, and then we're going to square it. We're also going to find the mean of our y values, and then we're going to find the distance between the y and the mean. And then we're going to find the distances, those mean differences squared. So here's our values. Now, they actually, our formula is the actual minus our predicted, where they did it just the opposite, and they did the predicted minus the actual. But it really doesn't matter. If we were doing the residuals, all these signs would be different, would be the opposite. But when we square it, which is what we're looking for, they're all going to be positive anyhow. So we square our residuals and add them together, and we get this sum. The mean was 25.2. So to find the distance between y values and their mean, take the y and subtract the mean, and that's how we got these values. Then the mean distances squared. Just take that value and square it. Find the sum of those, and it's 855.6. Okay? So that's how we calculate all of those things that we need. All right? So, to calculate R squared, remember, it is the sum of the distances between the actual and the predicted, or the sum of the residual squared. So 1 minus the sum of the residual squared over the sum of the squared distances between the actual y values and their mean, or the sum of the quantity of y minus the mean quantity squared. And when we do that, we get 1 minus 91.81 over 855.6. So 1 minus 0.11, and it's 0.89. Okay, so how well did that predict? Don't get mad at me. Don't kill me. Remember, this was the data and the graph that we were finding r squared for. The value we got was, for r squared, was 0.89. Now remember that this is written as a percent. This would be 89%. So here's the shortcut to r squared. But we square the r, and we get 0.89. Of course, we'll be using calculators too. All right. So, to determine how well a regression line fits the data, we find the value called r squared. To find r squared, simply square the correlation. The closer r squared is to a positive 1, the better the line fits the data. So r squared is always a positive number because we're squaring it. Okay, so that first line had an r squared of 89, which means that 89% of the variation of this data can be accounted for by the linear model. R squared for our other set of data was 0.62 or 62%, and therefore only 62% of the variation is accounted for by this data. So therefore the first model was better than the second model.